And the way it's usually set up is it goes to a terminal board. So this is the so this down here is the actual PLC. And these are the inputs to the PLC. What's nice about a PLC is you connect the inputs up, and then when you create your program, you hook them in parallel, you hook them in series inside the program. So all your inputs are hooked up basically the same. And this is the terminal block that's at the top. So this is just a terminal block. So are these syncing or sourcing? So this is DC. These guys, both our lines are on, the inputs are powered by 24 volts DC and the outputs are powered by 24 volts DC. So are these syncing or sourcing? Are these switches wired syncing or sourcing? Well, here's the plus right here. So here's the minus. So this terminal block has both plus and minus available to us. So the plus goes out to the switch. So that means these guys are wired to source. And then of course this comes in here to the PLC. So the PLC is connected to sync. Does that make sense? Okay. So yeah, so these PLCs run syncing. On the 3-wire sensors, it gets kind of confusing. Let me just tell you what that. So these are all push buttons, or these are all switches, manual operated switches, momentary contact. With this guy right here being a e-stop switch that latches e-stop switch. So that means once you push it, you have to do some of your e-stop switches, you actually have to push them in and turn them and pull them out. These you just can pull them out. So they have different types of e-stop switches. Usually they have what they call a mushroom head on it, which is real big. So you can see, and it's red, right? So you can see it, real easy. I think those, the e-stops are actually in the ceiling, and they have these ropes all the way down through there that if something happens, so you can just do, pull one of the ropes, if I remember right. Yeah, it's pulled. Well, I don't know how the e-stop switch works, but you pull the rope, to initiate the e-stop. So, this is, some actual sensors. Oops, where am I at? So these are some sensors, and so what we do on these is we identify what type of sensor it is by what's inside the symbol. So the symbols are actually in a square, and then the little diamond shape indicates that it's a proximity sensor. And then this guy right here identifies what type of sensor it is. I don't know why they got the line split, but what they do is they put this guy right here. You can see this. And then this is usually filled in. This means it's some type of magnetic sensor. It's not magnetic, it senses magnetic. So we see 3-wire sensors. We know the numbering system now. We know that your odd numbers are power and your even numbers are signal. So we come up here and we see this guy's connected to plus, and then 3. So this would be ground, right? And then this guy is connected to, 3 is connected to minus, so this guy right here would be blue. And then 4. So looking at this guy, I don't know if it's what. I don't know whether it's syncing or sourcing. So it's very, very important that you know that, because 3-wire sensors, both of them hook up to L1 and L2, right? You understand that, or plus and minus. We can tell on this guy, so this is, I know this guy right here is a Hall effect. And I know this right here is a reed switch. How do I know that? Well, one of the 2-wire sensor, one of the 3-wire sensor. The Hall effect does not have to be powered. All it is a switch, right? It's a magnetically controlled switch. So this guy's got 2 wires. So this would be, this is pointing, now instead of connecting to L1, it's pointing, it's pointing toward the minus, right? Or pointing toward the other side. So that would be brown on the top, blue on the bottom, right? And then this goes to the PLC. So I know, and it's connected as sourcing. So I know the PLC is connected as syncing. But if you got all these 3-wire sensors connected up to a PLC, you got to know what the PLC uses, right? You understand, before you order the right one. Make sure you order the right sensor. Because if you got a 3-wire sensor, you don't know if it's what? Syncing or sourcing. Because you got 1 wire connected to L1, you got 1 wire connected to L2, unless you look at this wire right here. So this wire right here is going to be what? That still don't tell you that. Sorry. It still don't tell you. So you just don't know on a 3-wire sensor whether it's syncing or sourcing by doing what? By looking at the wiring scheme, because a sourcing sensor would be exactly the same as a syncing sensor. So you need to understand what your PLC or your program controller actually does. So all these are magnetic sensors. I don't know if they got any more in here. Let me find the original prints. Yeah, so this is a photoelectric sensor. This is a pressure sensor. So this guy here has a pressure sensor on it. And these are the outputs. These are directional control valves. So these are the outputs. Need to find another one that's got some what kind of sensor is this? P1. Yeah, that's a capacitive sensor. And what can capacitive sensors pick up? They can pick up solids, right? Most material. What's this guy right here, B4? That's an inductive sensor. This is a photoelectric sensor. So this has got 2 capacitive sensors on it. It's got an inductive sensor, photoelectric. And like I said, if all you got is 3-wire sensors, you're gonna have to know whether it's DC. Of course, ours are AC. We're honoring the color code, even though technically you could swap the what on ours since ours are AC. You could swap the brown and blue wire because it's AC. AC has no polarity. But we're honoring the right color code, so we're making sure we hook the brown wire toward L1 and the blue wire toward L2, right? You understand that? Or 2 L2 on a 3-wire sensor, just to keep everything standard. So that shows you all the different symbols. Now, this is not all of them. This is just the ones that we have on our manufacturing line. So I was going to try to look up and see if there was a IEC symbol for a temperature sensor, which we use, and also a solid state level sensor. Our level sensor is not solid state, so it will use the standard electrical control symbol. So what we're going to do, so everybody okay? So y'all got that? These symbols will be on the test. Very, very important to understand symbols. And why is that? Well, if you don't understand symbols, you can't read print. And you can't draw prints that other people can read, right? You understand that? Huh?
You can't look it up the right way.
Oh, yeah, you might not have to get it the right way. That's exactly right. So, that's a good point. But you couldn't read the schematics, right? Or the diagrams to So I could bring up the ones for the Festo line, and you'd see that it's very, very similar on how these things are hooked up. We don't hook them up in parallel. We don't hook them up in series. We hook up one device per input, and then we write our program. Some of y'all have had PLCs. And what's nice about a PLC is all these sensors can only have one contact. And inside our program, we can make it control as many contacts as we need. So PLCs are becoming the norm now, guys. So we still have electrical circuits, and it all works down to cost. So there's still electrical circuits out there. It all works down to cost. Which one is more cost effective? You know, if I just want to hook up one standard little circuit, I'm not going to pay all this money for a PLC and then plus all the money to write the programs for it, if I can do it, if I can hardwire. Okay, so what we're doing today is we're moving into level sensors. So we'll look at distance and level sensors. They're basically the same thing. A device capable of responding. Of course, this is the definition for a sensor. So a lot of people call them transducers, but that's not exactly true. So a sensor is a transducer, but a transducer doesn't have to be a sensor, right? You understand that? So we looked at position, we looked at speed. We skipped over weight, by the way, because we wanted to get into the lectures for our lab. So probably the next thing we'll look at will be pressure. So now we're going to look at level sensors. So I've changed the way the course is laid out. So distance is the amount of space between two things. Level is the amount of vertical distance, height from ground or another stated or understood base. The height at which one material begins and another material ends or stops. These are two terms that that handout gives you. So what you got there, you got the supplemental for the level sensors. And of course, this is yours, right? That's basically your textbook for this class. And it starts talking about when we deal with level, and this is mostly level sensors, is that we're going to have what we call a charging system. So we're going to wire 3 different labs in here. And there's no design project in this lab, by the way. And that's something y'all need to think about, is that these labs are going to be scaled a little bit, not much because we don't have that many labs, but by at least one lab. So if you get to that design project and you're taking all this time to do it, what do you think you might need to do? What? Tip it and move what? Move on to another lab. And then if you have time at the end of the term to do what? Come back and work on it. So we can do these labs in any order. It's just that I don't want to give out labs until we lecture. So there's 3 labs inside each section. And by the way, the checkup that's at the end of the lab section These are now online, so you don't have to turn those in, right? You need to do them online. They're inside the section. I'll make sure before we leave that before we get through the lecture that I show you exactly where these are. So these labs run in groups of threes, and then after lab 3, there is a multiple choice checkup, kind of like multiple motor controls. But what I've done is I moved those to online, so it'll grade them for me. Plus, I can make some corrections that are actually in the okay. So first thing we'll look at is ultrasonic. Converts ultrasonic waves into electrical signals and vice versa. And what it does is the sensor measures the time interval between it, so it generates a pulse. A lot of you can actually hear them kind of click. It generates a pulse, and then it measures the amount of time that it takes for it to reflect back off a surface. These are very reliable. Radar works on the same principle. It's just that a radar is a a lot higher frequency. But that's what it does. So if you ever been pulled over by the police and they stopped you, you don't see many police anymore. Thank goodness on the roads because I get pulled over a lot. But this is what they do to check your speed. They use ultrasonic. We have a transceiver is a term we use for one unit that contains both the transmitter and the receiver. So technically these are called transceivers. They can be digital or they can be analog. So digital, we're going to look for it at a precise level. Analog, we're going to look for it over, we'll actually measure the level, right? So your level sensor in your automobile fuel tank, is it digital or is it analog? Analog. Well, technically it's both. Because most cars now have a light that comes on that says what? When it's low, right, it tells you to get gas. And then another one actually gives you the gas level. So technically it's both. Don't everybody have a light that comes on? When I had a Honda Shadow. It didn't have a gas gauge on it. It had a light came on, which I liked. My Harley didn't do that. It had a switch on the side, so it had a 2-level tank. So it had a spacer, and it had an upper level and a lower level, and we got down below the lower level, your bike would start doing what? Stuttering, and you'd have to reach down by your leg and turn it over to the reserve. And then you had to remember to turn it back when you filled it up. So I ran out of gas one time because guess what I didn't do? I didn't switch it back to, I kept it on reserve, so I ran over there. Luckily I was close to the house. So odds are if you're driving and you see a guy on a Harley pulled over on the side of the interstate, odds are he or she did the same thing. Can be designed to sense distance, movement, level, or solid or liquid, speed, or direction. So ultrasonic sensors are very, very versatile. We ran into this in the hospital a lot where they can literally not use x-rays, but they can use ultrasonics to actually penetrate the skin and go in and look at different things. Like babies, when they're early, and also, I was on my back so much when I had my motorcycle wreck that they checked me every once in a while to see if I was getting blood clots in my leg, and that's what they use ultrasonic. So ultrasonic distance sensors. So if you've had robotics, the distance sensor that actually looks like 2 eyeballs, in intro to robotics, that's an ultrasonic sensor. And that is not digital, it's analog. You make it appear to be an analog sensor by setting a threshold inside the program. But you can set that threshold anywhere between 0 and... Photoelectrics, we have what we call triangulation. So what these do, these sends out a light, and then it reflects back, they transmit a light, it reflects back at an angle, and then they measure the angle, and this would determine the distance. So the mouse is kind of like that. So when you look at a mouse, you can see that it's at an angle. This is actually what we call a definite reflective, because it's not measuring the distance, it's at a certain distance. So that means if I come up here and I just move it up off the table just a little bit, it don't do well. Because it's looking for those surface impurities at a precise angle. So this is a triangulation photoelectric sensor. So it shoots out a beam and then it measures the reflected angle and whatever reflects back. This would be the angle of. This would give us the distance. Are we okay? This makes sense. Pretty straightforward. Time of flight photoelectric sensors. These work exactly the same as ultrasonics. This has to be a reflective surface. So what this does, it transmits a light, and then a light pulse, and then it times how long it takes for it to reflect back to the receiver. So this is very similar to the way an ultrasonic sensor would work, but these are a lot. This uses light instead of a magnetic pulse. I'll get it out in a minute, guys. That's an excellent question. If you're dealing with reflective surfaces, and sometimes the problem with ultrasonics is that, and we could have the problem with light. So it all depends. So the problem with ultrasonics is what determines how good of a reflectivity. We got airplanes that fly through the air, and they basically can't be sensed by radar. So how does that work? How in the world can a big old plane, a B-1 bomber, look like a bird on a radar? Well, first of all, it has no flat surfaces. It actually has no flat surface. So for it to reflect back, it has to be a flat surface. And then the material that they coat it with is radar absorbent. It actually it don't reflect back. It actually does what? It actually absorbs the radar. So it all depends on what you're looking at, what colors you're looking at. So that's a really good question, but what application do you want it to do, right? You understand? So it's a really good question. So light has problems too because it reflects back. How much light it gets back depends on the color that it's reflecting, right? You understand? So if the light beam was red, we would get a real good reflection off red, right? You understand? It wouldn't absorb the red. So it all depends on the application, where one would be better than the other. So that's a really good thing. So it all depends on the distance to the material that you're going to look at. So radar would depend on a flat surface, right? It would go on a flat surface. So ultrasonic level detectors. So what would this depend on is what it's trying to measure. If it absorbs it, then it's not going to be good, right? So a liquid surface might want to use something else. So that's a good one. Discrete level detectors and continuous level detectors. So this is covered in there. So this is basically what we're using. In fact, let me bring it up. This is our level detector. So and what's the symbol? What's the symbol for a level detector? Anybody know? So we put a dot, and then we draw a line. This would be normally open, and then we put a circle. This would be normally open. And then, of course, a normally closed would be drawn above the top. And this right here would be for a level detector. So this guy right here is using a float, which is very, very standard. So this is basically what's in most automobiles. I hadn't had the privilege of looking at the fluid of the gas detector for a while. It wouldn't be surprised. So our unit has two of them on here. So this is our float switches. So in the diagram, you'll use one of those two symbols, right? So this one, Pretty simple. And of course, this one right here. Now this one, and we'll look at this. These work off reed switches. So here's the actual switch coming off. And so inside, you can actually see the magnet on this one. So here's the magnet right here. And then of course, when it gets up close enough to the reed switch, it will trip it, right? You understand that? This one, the magnet is offset on one side. So if you want it to operate one way, you'll leave it. If you want to operate it the other way, so if you want it to be closed when it's down or open when it's down, you'll take off this little clip right here and just flip the whole thing around. But don't lose the little flip, right? If you decide to do that. So this one can be changed. This one depends on the way that the module is mounted. So if we mount it this way, then of course this would work like this. No, I don't even that won't work like that. So this is going to be mounted like this. I guess so. This will be a liquid. It comes up and hits it. That'll raise it. And like this, it would be the same. It would work. So this guy would work depending on which way you want to go. There's the actual magnet, and then of course the reed set switch is inside this too. So this would be kind of like the limit switch, but it's not going to hit a cam. This is photoelectric, where it shoots a beam across from a detector through the beam, right? But here's the material that's going to actually come up and block the beam. And then this other one is either a resistive probe or so a resistive probe basically has two rods, and then the material comes up in between the two rods. And there's very few materials, especially liquids, that have absolutely no resistance, right? So what this is doing is it's actually looking at the resistance to change between those rods. Are we okay? That makes sense? So we could also float. We could also use a pressure switch mounted at the bottom. That senses the pressure, so the higher the liquid, the more pressure it will produce. So we can use load sensors, which we'll talk about before long. So this is actually measuring the weight of the vessel. And as we fill it up, the whole weight of the vessel gets larger, gets more. And then, of course, we have electrical probes. This could be either resistive or capacitive. Capacitors are basically nothing but two plates that's divided by an insulator. And these guys operate off AC, so DC, they act like a little small battery that we charge up. But if we're going to use it in this thing, we're going to put AC across it. And its opposition changes with frequency. Everybody know the formula? We call it X of C, and it's in ohms. Anybody know the formula? Had AC? 1/2 pi FC. So we put a frequency across it, and it's going to be constant. And the distance between the plates are going to be constant. So what we do is we change the value of C. Now what determines the value of C is the size of the plate, how close to get the plates together, and then what we use as an insulator. So here what we're trying to measure is going to be the insulator. So as it goes up in there, the insulation, basically the more we get up inside the capacitive probe, the less opposition it'll have. These are exactly what we used on the airplanes that I worked on. They were big planes. They had a 5,000 gallon center tank, and then they had 2,000 gallon wing tanks. And we had these, and it was really neat because they sewn them all together. So we had multiple probes inside the wings And if the plane turns, then the inside would get more and their resistance would go down, and the outside would get less and their resistance would go up, or their opposition would go up and it would balance. So we use capacitive probes inside to keep to measure the fuel in all those tanks. So that's 9,000 gallons of gas. These planes could stay in the air for 14 hours before refueling. That was a lot of gas.
They have a lot of baffles.
Huh? Yeah, the baffles. That's a good point. Had baffles all down the wings. So these are just holes that don't allow the fuel just to do what, flop to one side. Yeah, there's baffles all the way down the wings where it had holes. They had plates and then they had holes in them. If you ever had a waterbed, that used to be very, very popular. So they had waveless, and that's what they used. They used a lot of baffles inside the actual bladder. A baffle is basically something that we use to limit the speed of the flow of fluid or air. A perfect example is your muffler. So your muffler has a lot of baffles in it. And basically the baffles in those are just different paths that the air has to go through. So what that means is that pop doesn't come out at the same time, and so it goes different lengths. So basically it's either veins or something that causes this thing to slow it out and spreads it out. So your muffler basically does that. When your engine pops, right, when it fires, it spreads to pop out, so it don't come on at one time. So in the airplane, inside the wings, they just had these guys and they just had holes all in it. So the fluid, instead of doing what? Yeah, if the plane was doing like that and all of a sudden it did like that and you had 2,000 gallons of gas going this way and 2,000 gallons of gas going that way, the plane would do that, but it was what? It was slowed down.
Sort of like a filtering type of thing that slows it down.
It slows it down. It doesn't really filter. The filter takes out stuff. It just slows the flow down. And like I said, you have a baffle in your car. We called it a what? A muffler. But what does it do? It makes the pop take different paths, and it just does what? It takes the pop and does what? Spreads it out. So yeah, there had to be baffles in all the tanks inside an airplane, because 5,000 gallons of fluid flopping to one side at the same time would be drastic. So good point. So capacitive sensors resistance just basically measures the resistance of the liquid, and the more it gets up in there, the resistance goes down. Right? You understand that? Basically, capacitive sensors do the same thing, but what they're doing is the actual material changes what we call the dielectric constant of the capacitor, which causes the capacitance to change. If the capacitance change, then the ohms change. If the ohms change, then we can come up with a transfer function that actually does that. So we had to calibrate these. So we had a test set that would go out and we'd hook up, and anytime we changed out a fuel cell indicator, we had to calibrate it for the cells, which was a pretty neat set. So we could do it even if the tanks were empty. And changing out the top capacitive sensors wasn't bad, but if we changed out the ones that were on the bottom, we'd have to drain the tank. We'd have to drain the tank also. That would be fun. So, and then of course you had different capacitive sensors at different lengths, depending on where they were in the. Yeah, for some reason these pilots like to know how much fuel they have in their tanks. That was one of the systems that I worked on, was the fuel system on the plane. So guys, that's about it. They're very, very simple. Ours is a like I said, ours is a kind of like this guy. But what ours uses, it actually has a reed switch on it. And then, it has a magnet on it. And then the reed switch just senses what and then these are the two white wires that come out. These are AC. There's no brown, there's no blue, so it doesn't make any difference. And it's obvious on this. You don't have to look up these on your handout that we have. So since it's AC, it makes no difference. Well, even if this was DC, it makes no difference because it's a switch, right? You understand? So it's pretty obvious. 1, 2 would be this one. 3, 4 would be this one. Like I said, well, these don't matter how they're mounted. All these spacing on our trainers are exactly the same, so you can mount these. You can mount them this way, you can mount them this way. So it all depends on the way the lab is written up. And of course, we have three labs, every section you got, and then the next ones we'll look after this would be temperature sensors, and that's all the sensors that we have to do labs on. So there's the motor control sensors are these symbols are up, should be in the handout section of Blackboard. Let's see. Johnny come in? Let's see, Grant came in. See back there. Scott's not here. Cameron, I don't know why I'm in description. I must have been off of. And Justin's not here. Oh, there's Justin. Everybody's here but Scott and Johnny. Huh? I think I got you. No, I didn't. There you go. Thanks, Lord. So in the course material content, and then in the reference material and handout section, relay logic, rules of relay logic. And by the way, some of y'all are breaking some of these rules that you got to be really careful about. So we're going to put these back on the test. And we're also going to do that on PLCs too. So some of y'all are breaking rules in there too. Here's electrical control signals, symbols. So we're interested in basically this section right in here. This section down here. This is standard symbol for a proximity sensor, right? A solid state proximity sensor. It don't show whether it's a 2-wire or 3-wire. Here's a liquid level switch or float switch. These are pressure switches. These are temperature switches. Switches. These are flow switches, and those are the main type of mechanical sensors that we use. So I need to start making sure you understand these right here. So if I have a programmable controller, your input devices are supposed to use the right symbol. Inside the program, basically we have very few symbols for contacts. We got 2 symbols for contacts. We have one for a examine if open and examine if closed, which are here we call them normally closed and normally open symbols. And every input device every mechanical or electronic input device uses those 2 symbols. So it's up to you is to use the correct symbol when you wire up the PLC, right? You understand that? So out here on the outside, you need to use the what? If I still have it open. Yeah. It's up to you to use the correct symbols out here. When it gets inside the PLC, when it gets back inside the PLC, all these guys hooked up to these inputs use 2 symbols. So inside the program, this would be we call this an examine if closed, and this right here would be an examine if open. Is that a magnetic reed switch? Is it a level sensor? Is it a distance sensor? It's all of them. That's who you got. So where you identify what type of sensor is on the wiring diagram for the PLC itself. Or you can give these things names. In PLC 1 we call them symbols. In PLC 2 we call them tags. So you give them a name, a physical name that might identify what it is. But it's very, very important to learn symbols because these are the diagrams that you'll have drawn up, right? You understand that? So anybody, we'll go ahead and